Hello, this is Jack Jackson with part 13 of our series of lectures on discrete probability. This is on geometric distribution. And by the way, we're also going to be looking at the Bernoulli distribution as well at the beginning, because the geometric distribution is kind of based on the Bernoulli distribution, and the Bernoulli distribution is also the basis for the binomial distribution that we're going to study in our next section. So let's start by looking at the Bernoulli distribution. And by the way, Bernoulli is a name of actually a whole family of mathematicians. There were at least two generations of the Bernoullis that were very, very famous, and multiple people in both generations that were very famous as mathematicians and scientists, and you'll hear that name show up a lot in various fields, and in particular, here it is in probability. So, consider the experiment of rolling a single die. We will call a success if we roll a 5 or 6. We'll let x be a 1, x equals 1 if it is a success, and x equals 0 if it's not a success, which we'll call a failure. Go ahead and answer these questions here. What is the probability of success? We're going to call this P. What's the probability of failure, not a success? We'll call this Q. What's the relationship between P and Q? And then we're going to try to make a table and graph for this distribution. Go ahead and answer these questions now. Press pause. Okay, by now we should be able to answer these. Of course, the probability of success is 2/6 or 1/3. So P is 1/3. Q then is 2/3 because Q is always 1 minus P. If we make a table and graph for this distribution, there are only two values for the random variable, either 0 or 1. So our table only has two x values in it, 0 and 1. The probability of 0 is 2/3 or 0.6 repeating. Probability of 1 is 1/3 or 0.3 repeating. And when we look at our graph, we're going to have two bars, one above 0, one above 1, and the heights of those bars are Q and P. The height of the bar above 0 is Q, the height of the bar above 1 is P. So again, the idea of a Bernoulli distribution is we divide the sample space into two outcomes, one of which we call a success and everything else is called a failure. Let x equals 1 when there's a success, x equals 0 when there's a failure. P is the probability of success, Q, which is 1 minus P, is the probability of failure. And the graph is just two bars on the PDF with heights Q above 0 and P above 1. And the mean of the distribution, well, let's go ahead and figure that out. Remember, the mean of the distribution is the expected value of x. That is, you take the x value times the probability of that x value for all the different values of x and add them up. Well, we just got two things here, so it's pretty easy. The first one we're going to look at is 1 as a random variable, and the probability of 1 is P, plus the other random variable value is 0, and the probability that you get a 0 is Q. So 1 times P plus 0 times Q reduces to just P, so the expected value or mean of this distribution is P. So if you were to do this a lot of times, on average, you would get P would be the value of the random variable, average value. The variance turns out to be P times Q. Now let's see if we can see that by looking at the computations over there on the right in black. So remember, variance is sigma square, and that's the expected value of x minus mu square. Again, we plug in our different values for x, 1 and 0, and we get x minus mu square, and then times the probability of x and add those up. So we have 1 minus P square. First of all, remember mu is P, so we can substitute P in place of mu, and we're substituting 1 in place of x, and then we have multiply that by the probability of 1, which is P. Plus, now we put in 0 for x, 0 minus mu is still P, 0 minus P square, times the probability of 0, which is Q. So let's simplify a little bit. 1 minus P is, another way to say that is Q. So the first part, the first term, is Q squared times P. Plus, let's see, 0 minus P is negative P. Squared, it's the same thing as P squared. So the second term is P squared times Q. Both terms have both a P and a Q as a factor, so I can factor that out using the distributive property or common factor factoring, and we can factor out a PQ. What's left is Q plus P. Of course, you can distribute that back out to check that. But wait a minute. Q plus P is just 1, and 1 times PQ is PQ. And so we know that the variance is PQ. And of course, the standard deviation then would be the square root of PQ. If we do the Bernoulli experiment one time, it's called a Bernoulli trial, and we will use Bernoulli trials, particularly several of them in a row, to build up other kinds of distributions, in particular a geometric and a binomial distribution. We're going to study the geometric distribution for the rest of this lecture, and we'll study binomial distribution in the next lecture. So here we are for a geometric distribution. We want to perform independent Bernoulli trials until the first success happens. We let x be the number of trials until the first success. So notice we don't know ahead of time how many trials we're going to make. We do know how many successes we're going to have. Exactly one. The last one we try is a success, then we stop. Okay? Now that may happen on the first try, it may happen on the second. It may take us 15 tries for it to happen, but once we get a success, then we stop. And what we don't know is how many trials we'll get. We'll get one success and x minus 1 failures for a total of x trials altogether until we get that first success. So let's look at an example. Suppose we roll a single die and it's a success if it's either a 5 or 6. In other words, just the same thing we looked at in our Bernoulli trial just a minute ago. So we want to repeat this Bernoulli trial until the first success, counting the number of trials along the way, and let x be the number of trials until the first success. That will be one actual application of this experiment. So remember, you may have to roll a bunch of times and count them, but all of that until you get the first success is really just the experiment one time. So when you get your first success, record the value of x, and you've completed the experiment one time. Then do it again, record your value of x, and so forth until you get a total of 20 x values, and make a table and graph of your empirical results. I think it's really important for you to actually physically do this, actually get a die out and do it, or if you don't have a die, use the simulator on your calculator. A couple ways you can do it. You can do it by actually rolling the die on the probability simulator, or you could do it with a coin on your probability simulator, but you have to make sure it's an unfair coin. You have to adjust the probabilities so that the probability of a heads, let's say, which is a success, would be 1/3, and probability of tails, which is a failure, would be 2/3. So anyway, I think it's important that you do this actually yourself so that you get a good feel for what kind of experiment we're talking about. So go ahead and do that right now. Press pause. Okay, well now you're back, and hopefully you've done that experiment. Now let's actually look at the theoretical results of what it should be for this experiment. So we're going to repeat the experiment until the first success. X is the number of trials. What are possible values for the random variable x? Well, x can be any natural number, 1, 2, 3, 4, 5. Notice you can't get 0 or negative, but there is really no upper limit to this. They get less and less likely as we go out there, but there's still some very, very small, perhaps, probability that x could be a very, very large number, as large as anything you'd want to put in there. So in theory, this goes on out forever. In practice, the probabilities get so small out there pretty quickly, perhaps, so that they're not very likely to happen. But the actual domain, or the output for the x value, is all the natural numbers, and of course that is the domain or the input for the PDF. So, even though the x values go on forever, we can't physically write down the entire table or draw the entire tree, but we could start it. We could draw the first part of the tree, or the first part of the table. Let's do this. Go ahead and draw the tree out for the first 5 x values, and then make the table out that goes with it for the PDF. And actually graph the PDF as well. Go ahead and figure that out. Press pause now. Okay, let's take a look at the tree. So notice at the beginning we can either have a success or a failure. You have a probability of success is P, probability of failure is Q. Then the next time it's an independent Bernoulli trial, so again we have a probability of success or failure the next time if we had a failure the first time. If we had a success for the first time, we're done. And the probability of that path is just P, in this case 1/3. But the next time, if we have a failure the first time, we roll the die again. we might get a success or failure. If we get a success, we stop, and that happens with probability P, but that means the probability of getting a failure and then a success in that order then is 2/3 times 1/3, or 2/9. That's P times Q. Now, what if we got a failure the second time? Then we go again. Once we get a success, we stop. Okay? And so the next time we roll a die, we could get a success with probability P, or failure with probability Q. If we get a success, we stop. And notice what we've got. We got 2 failures in a row, then a success. So when we multiply that out, it's 2/3 times 2/3 times 1/3, or in other words, P times Q squared, which in this case is 4/27. What if we get a failure? Well, then we have to roll again. We might get a success or a failure. Again, these are independent trials, so every time the probability of success is 1/3, the probability of failure is 2/3. Now look at what we have this time. We have failure, 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 success. That's 3 Q's and 1 P all multiplied together, so that's P times Q cubed, or in this case 8/81. And finally, if we do a success the 5th time, we're going to get 4 failures in a row followed by a success. So when we multiply those probabilities out, that's P times Q to the 4th, which in this case is 16/243. Now, of course, this tree actually goes on forever, but I think you can pretty much see once you've gone this far what the structure is going to be on this table, of this tree, and of course the table and the formula as well. So notice each one of these has just a P, 1 P, that's the last branch is always P, and then however many failures you have, which is x minus 1 actually, you'll have that many Q's. Okay, here's a decimal approximation written in percentage form of probabilities. This is a PDF is a probability that x equals the k value that you see input here on the left, and I've worked them out up to 10. And on the right we have the cumulative density function, the probability that x is less than or equal to k, and we've got those worked out as well, rounded off to several decimal places there. Here's what the graph looks like. That first bar has height P. The second bar is P times Q. Now remember, Q is a number less than 1, as is P. And so when you multiply a number by a number less than 1, the value, a positive number less than 1, the value is going down. Okay? And so now the second bar is P times Q, which is shorter than the first bar. The next one is P times Q times another Q. So each time we're going to the right one on the table or right one on the graph here, right one bar, we're multiplying the previous bar by Q. This is exactly what's meant by an exponential function. I'm sure you studied those in your algebra class. And if we have an exponential function that's domain is only the natural numbers, or perhaps the whole numbers, then we call that a geometric sequence. So a geometric sequence and an exponential function are basically the same thing, except that a geometric sequence has a domain only the natural numbers. Well, if you think about it, that's exactly what we have here. We have a sequence. There is no x value of 1.5 or pi or 5.7. You only have x values of 1, 2, 3, 4, 5, 6, 7, 8, 9, and so forth. And this is exactly what's meant by a geometric function or geometric sequence. And so there we go. We have a geometric sequence, so this is called a geometric distribution. So it's basically just an exponential decay function, with the domain being only the natural numbers. So, whoops, let's go back. And so what's the probability that the random variable x equals some k value? Well, you always have 1 p, and then you have k minus 1 q. So it's p times q to the k minus 1. Or we might say that p of x is just p times q to the x minus 1. And so that is exactly an exponential type formula as well. Now, we can compute the mean and variance in the cumulative density function for this one. The PDF is the probability that x equals k is p times q to the k minus 1. The CDF is the probability that x is less than or equal to some number, let's say m. That's the sum from k equals 1 to m of p times q to the k minus 1, and that turns out to be 1 minus q to the m power. The mean of this distribution turns out to be just 1 over p, and the variance turns out to be q over p squared. Now, finding these last three formulas, the one for the CDF, the mean, and the variance, actually requires a little bit more advanced mathematics that I don't really have time to go into at this point. Typically, a course where you would see this mathematics would be like a Calculus 2 class. But the formulas that we come up with are pretty easy. So I'm not going to show you how we got these formulas. I guess you just have to trust me that these are correct. But they're very simple formulas once we get them. And so we could use these if we wanted to find the mean and variance. Or even the CDF is a nice little formula there. That's pretty nice because we can use that formula rather than adding, like if we wanted to be the probability that x was less than or equal to 3, rather than figuring out it for 1, 2, and 3, the PDF, and then adding all those up, we could just use this pretty simple formula here from the CDF. So it's a pretty nice little formula. Okay, let's put this to work in an example. Suppose that 1 out of 15 people test positive for a particular strain of flu. What's the probability that the fourth person you test will be the first one to test positive? See if you can figure that out. Press pause now. Well, notice that the probability of each person testing positive, they're all independent. We're assuming they're independent, there at least. And that p equals 1/15. And we're finding the probability of the first success happening on the fourth trial. So this is a geometric distribution. We're counting the number of not the number of successes, the number of trials until we get one first success. So we're looking at the probability that x equals 4. It's p times q to the third power. It's 4 minus 1 is the power on the q. And of course that would be 1/15 for p and 14/15 for q then, because q is just 1 minus p. And so we get 1/15 times 14/15 to the fourth. So that's actually 15 to the fifth in the denominator and 14 to the fourth in the numerator. And that reduces to approximately 0.054202469 or about 5.4%. And of course we can do this pretty much directly, easily on the calculator. Parentheses 1 divided by 15 parentheses times parentheses 14 divided by 15 parentheses power 3, enter, boom, we got the whole thing. It turns out, however, though, that the geometric probability distribution is actually already built into the calculator. This one's pretty easy to do without the built-in shortcut, but that does have one. It's kind of nice. So this turns out to be the geometric distribution PDF, and to identify which geometric, you have to tell it what the p-value is, and then we're going to evaluate that at some k, x equals k value. So the syntax is we want to type in geometric PDF, put in your p-value of 1/15 and your x value or k value of 4, and we could get it. You see here the buttons that you're going to push on your calculator. Second, variables, which is actually has distribution written above it. Up arrow twice will get you to E here, which is geometric PDF. And go ahead and hit enter, so geometric PDF parentheses will show up on your screen. Type in 1 divided by 15, so that's your P, comma, then 4, close parentheses, and enter, and it will find out that. So the syntax is geometric PDF, give it the p-value, comma, the x value. And that will be probability that x equals that particular x value on this particular distribution. Again, suppose that 1 out of 15 people test positive for a particular strain of flu. What's the probability that the first person to test positive will be among the first 7 people tested? In other words, what's the probability that that the first person tested will be on the 7th one or less? So that's the probability that x is less than or equal to 7. So what you want to do is find the PDF, the geometric PDF, and add it up from k equals 1 to 7. Okay, but again, this one is built in. We actually had a shortcut formula up above, but really you don't even need to know that because you can use the calculator again. So geometric CDF, again you put in the P and the K, but this time it's a CDF, a cumulative distribution function, and it turns out to be about 38%, as you can see there. Go ahead and try these on the calculator. Make sure you've got these to work out. Try the geometric PDF and CDF. Go ahead and press pause. Okay, now that you've tried those out, let's go on.